You are listening to Data Flow Unlocked, a beginner's guide to ETL processes and data pipelines. Like and subscribe to keep up to date on our latest audiobooks. Data Flow Unlocked, a beginner's guide to ETL processes and data pipelines. Chapter 1, Deconstructing Data Flow. What are ETL and data pipelines? Our digital world runs on information. Every transaction, every click, every sensor reading contributes to a staggering volume of raw data. But raw data, much like crude oil, isn't immediately useful. It needs to be refined, processed, and channeled to where it can provide value. This is where the powerful concepts of ETL processes and data pipelines come into play. Think of it like preparing a meal. You start with raw ingredients, your data sources. Then you clean, chop, mix, and season them, the transformation. Finally, you serve the dish on a plate for consumption, loading the data into a usable format. ETL is precisely this culinary process for data. Let's break down the acronym ETL one step at a time. E for extract, getting the data out. The first step in any data journey is to gather the raw materials. Extract refers to the process of copying or retrieving data from its various source systems. Just as you'd gather ingredients from your refrigerator, pantry, or a grocery store, data is pulled from different places where it currently resides. These sources can be dozens of different systems within a single company. Imagine data sitting in a sales database, customer information in a separate customer support system, website analytics in another, and product details in yet another. The extract phase is all about reaching into each of these sources and pulling out the relevant data points. This information might be structured neatly in tables, like a spreadsheet, or it might be less organized, like a stream of text from a chat log. The primary goal here is simply to get a copy of the data from its original home without altering the source system itself. T for transform, making data usable. Once you've extracted the data, it's rarely in a perfect state for immediate use. This is where the transform phase becomes crucial. This is the heart of the ETL process, where the raw data is cleaned, refined, restructured, and enriched to meet the specific requirements of its destination. Consider our cooking analogy. You've got your raw ingredients. Now you need to peel potatoes, chop onions, dice carrots, and mix them together, perhaps even cooking some elements before combining them to create the desired dish. Data transformation is similar. You might need to cleanse, remove errors, duplicates, or inconsistencies. For instance, correcting New York written as NY or fixing typos in customer names. This is often likened to the garbage in, garbage out principle. If you accept bad data, you'll get bad insights. Standardize. Ensure that data follows a consistent format. Dates might be written in different ways, e.g., 1/15/2023 versus January 15, 2023. Standardization brings them all to one format. Aggregate. Summarize data. Instead of individual sales transactions, you might want the total sales per day or average sales per region. Join, combine data from different sources. You might merge customer names from the customer support system with their purchase history from the sales database to get a complete customer profile. Enrich, add new, valuable information. Perhaps you take a customer's address and add their demographic data from an external source, or calculate a customer's loyalty score based on their purchase frequency. The transformation phase is where data truly takes shape, becoming accurate, consistent, and ready for analysis and decision-making. L for load, putting data where it belongs. Finally, after the data has been extracted and transformed, it needs a home where it can be accessed and utilized. The load phase is about delivering the prepared data to its designated target system. This destination is typically where the data will be used for reporting, analysis, business intelligence, or even to power other operational applications. Common destinations include data warehouses. These are specialized databases designed to store large volumes of historical, processed data optimized for querying and analysis. Think of them as highly organized archives built for answering complex business questions. Data lakes. These can store huge amounts of raw data in its native format, often before it's fully structured. They're like vast digital reservoirs where data can be stored for various future uses. Operational databases. Sometimes, processed data needs to be loaded back into a system that applications use directly, perhaps to update a customer profile or an inventory count. Reporting tools and dashboards. Data might be loaded directly into specialized tools that generate visual reports and interactive dashboards for business users. The load phase ensures that the hard work of extraction and transformation culminates in accessible, actionable data for those who need it. Beyond ETL, embracing the pipeline concept. While ETL describes the three fundamental sequential steps, the term data pipeline often describes the broader, more encompassing journey. Imagine a set of interconnected pipes, valves, and pumps, all working together seamlessly to transport water. A data pipeline is similar. It's a series of automated processes that reliably move data from one system to another, often involving ETL steps along the way, but also potentially other actions. The continuous flow, automation, and orchestration. Early ETL processes were often manual, one-off tasks. Someone would run a script or a program to extract, transform, and load data periodically. Modern data pipelines, however, are designed for automation. They are scheduled to run at specific intervals, hourly, daily, or even continuously, ensuring that data is always fresh and available. This automation is achieved through orchestration. Think of an orchestrator as the conductor of a symphony. It's responsible for managing the sequence and dependencies of different tasks within the pipeline. For example, you can't transform data until it's been extracted, and you can't load it until it's transformed. An orchestrator ensures that each step executes in the correct order, handles errors, and retries failed operations, making the entire flow reliable and self-healing. Without orchestration, a pipeline would easily break down at the first sign of an issue, requiring constant human intervention. Why pipelines matter: reliability, scalability, timeliness. Well-designed data pipelines bring immense value to organizations. Reliability. They provide consistent, accurate data delivery, reducing the risk of human error and ensuring that reports and analyses are based on trustworthy information. Scalability. As data volumes grow, pipelines can be designed to handle increasing loads without breaking down, scaling with the business needs. This means you won't have to rebuild your entire data infrastructure every time your business expands. Timeliness. Automated pipelines can deliver data quickly, sometimes in near real time, enabling faster decision-making and allowing businesses to react to events as they happen, rather than days or weeks later. A day in the life. Simple examples of ETL in action. Let's look at a couple of everyday scenarios where ETL and data pipelines are silently at work, making our lives easier or businesses more efficient. Your online bank statement. Every transaction you make, deposits, withdrawals, purchases, generates raw data in the bank's operational system. Overnight, an ETL process extracts these individual transactions. It then transforms them by categorizing expenses, e.g., groceries. Utilities, calculates your running balance, and aggregates them for your statement period. Finally, it loads these neatly organized records into a system that generates your easy-to-read monthly statement or updates your banking app. A customers who bought this also bought recommendation. When you view a product online, the e-commerce system has a data pipeline running behind the scenes. This pipeline extracts thousands of customer purchase histories and browsing patterns. It then transforms this raw behavior data by finding patterns and associations between products, e.g., people who buy coffee makers also often buy coffee beans. Finally, it loads these insights into a recommendation engine that suggests other items you might like, enhancing your shopping experience and driving more sales. These everyday examples illustrate that ETL and data pipelines aren't just obscure technical terms. They are the fundamental mechanisms that make our data-driven world function. They are the unseen rivers, constantly flowing, constantly transforming, constantly delivering the lifeblood of information to where it is needed most. This foundational understanding of how data moves is crucial. In the next chapter, we'll dive deeper into the raw materials themselves, exploring the different types of data and where they typically reside. Understanding your ingredients is the first step to becoming a true data chef. Chapter 2, The Source Code of Information, understanding data, its types, and where it lives. Before we can extract, transform, or load data, we must first understand what data truly means, in what forms it exists, and where it's typically stored within the digital landscape. If data is the lifeblood of an organization, then understanding its various properties is like understanding the different blood types, their composition, and where they are produced within the body. Without this fundamental knowledge, any attempts to manage or move data will be akin to trying to solve a puzzle without knowing what the pieces even look like. Data's many faces. What is data in this context? At its simplest, data is a collection of facts, figures, text, or symbols that can be processed by a computer. In the context of business, it's any piece of information that describes an event, an entity, or a measurement relevant to operations. This could be a customer's name, address, and purchase history, a product's ID, price, and inventory level, a sensor reading from a factory machine, temperature, pressure, vibration, a log entry from a website, who visited, when, from where, and what they clicked, a financial transaction, amount, date, sender, recipient. The crucial point is that this raw data, by itself, often lacks context or is not organized in a way that allows for immediate analysis or decision-making. That's precisely where ETL processes and data pipelines step in. The big three: data types explained. Data comes in many forms, and recognizing these forms is essential because it dictates how we interact with them during extraction and transformation. We broadly categorize data into three main types: structured, semi-structured, and unstructured. Structured data, the orderly world of tables. Imagine a meticulously organized spreadsheet or a filing cabinet where every piece of information has its own labeled cubbyhole. Each piece fits perfectly into a predefined slot. Characteristics. This is data that conforms to a rigid, predefined model or schema. It's highly organized and resides in fixed fields within records or files. Think of rows and columns in a database table, where each column has a clear name, e.g., customer ID, product price, and a specific type of data it holds, e.g., number, text, date. Examples: customer records. Each entry has distinct fields for customer ID, first name, last name, email, phone number, date of birth. All customers follow this exact structure. Financial transactions. Transaction ID, date, amount, type, e.g., credit, debit, merchant name. Product inventory. Product ID, name, quantity in stock, price, supplier. Common source. Relational databases like SQL Server, MySQL, PostgreSQL, Oracle, traditional spreadsheets, e.g., Excel, and many legacy systems. Why it's important. Structured data is the easiest to store, query, and analyze using conventional tools because its format is predictable and consistent. Most traditional business intelligence and reporting relies heavily on structured data. Semi-structured data, some rules, some flexibility. Imagine a personalized postcard. It has a clear address section, which is structured, but the message area can be free-form text. The sender can optionally add a picture or not, depending on their preference. There's a general pattern or hierarchy, but not every piece of information is rigidly constrained into fixed fields, and some elements might be missing for certain records. Characteristics. This data doesn't fit into the rigid rows and columns of traditional relational databases, but contains tags or markers to separate data elements and build hierarchies. It implies a structure, but it's not strictly enforced by a predetermined schema that all records must follow. The structure might even be self-describing, meaning the data itself contains hints about its organization. Examples: JSON, JavaScript object notation, widely used for web APIs and configuration files. It uses key-value pairs and arrays. For example, name, Alice, age, 30, hobbies, reading, hiking. Another record might omit hobbies entirely. XML, extensible markup language, used for data exchange, configuration, and document formatting. For example, customer name Bob/named123/ID/customer. Log files often contain a mix of structured fields, like a timestamp and an error level, and free-form, unstructured messages documenting events. Emails have structured fields, to, from, subject, date, but also a free-form body text. Common source. web services, APIs, sensor data, configuration files, message queues, and some modern databases designed for flexible data models, often called NoSQL databases. Why it's important? It offers more flexibility than structured data, crucial for integrating systems that don't have perfectly aligned schemas. It's a bridge between the highly organized world of relational databases and the completely chaotic realm of unstructured data. Unstructured data, the wild frontier. Imagine a collection of handwritten notes scribbled on various pieces of paper, random audio recordings, a pile of photographs, or a video of an event. There's no inherent organizational pattern, fixed fields, or obvious schema that a machine can easily discern without advanced processing techniques. Characteristics. This data lacks a predefined structure or data model. It's free-form and doesn't conform to any specific format. It makes up the vast majority of data generated today because it includes content created by humans or highly complex sensor outputs. Examples: text documents, emails, the body content, reports, presentations, articles, research papers, social media posts, customer reviews, legal documents. Media files, images, audio recordings, video files. Email content, the main message body of an email. Sensor data, raw telemetry, often a continuous stream of unparsed bytes from various devices. Common source. Document management systems, social media platforms, surveillance systems, email archives, audio-video recordings, Internet of Things, IoT devices. Why it's important. While challenging to process directly with traditional database tools, unstructured data often contains incredibly rich and nuanced insights. Extracting value from it often requires advanced techniques from areas like natural language processing, NLP, for text, computer vision for images, or machine learning models that can identify patterns within the chaos. Where data resides, common sources. Understanding data types also means understanding their common habitats. Data can live in a multitude of systems, each designed for specific purposes. When we talk about extracting data, these are the typical places we're pulling information from. Databases, the heart of many systems. Transactional databases, OLTP, online transaction processing. These are the backbone of live applications, designed for rapid, frequent reads and writes of small amounts of data. Think of databases powering your online banking, e-commerce site, where your orders are instantly recorded, or customer relationship management, CRM, system. They typically store structured data. Examples: MySQL, PostgreSQL, Oracle, SQL Server. Analytical databases, OLAP, online analytical processing. These are optimized for complex queries and analysis of large volumes of historical data, often found within data warehouses. They are built for reading and summarizing vast amounts of data quickly, rather than frequent small updates. Examples: Snowflake, Amazon Redshift, Google BigQuery. Applications and APIs, the digital connectors. Many applications, like your CRM software, enterprise resource planning, ERP system, or even popular social media platforms, serve as rich sources of data. Often, these applications expose APIs, application programming interfaces. An API acts as a standardized way for one software program to communicate with another. It's like a waiter in a restaurant. You make a specific request, e.g., get me all new customer signups from today, and the API fetches the data for you from the application's underlying storage, usually returning it in a semi-structured format like JSON or XML. Files and documents, from spreadsheets to sensor logs. Not all data lives in highly managed databases. Many organizations still rely on spreadsheets. Simple, powerful, but can become unwieldy for very large datasets and difficult to manage in an automated pipeline. CSV, separated values, /txt files. Plain text files where data fields are separated by a delimiter, like a comma. They are common for straightforward data exchange between systems. Log files. Records of events generated by software applications, servers, or networks, containing information about system activity. They often contain a mix of structured attributes, timestamp, event type, and unstructured messages. XML/JSON files. flat files storing semi-structured data frequently exchanged between web services or used for configuration. Proprietary document formats, PDFs, Microsoft Word documents, image files, JPEG, PNG, audio files, MP3, WAV, and video files, MP4, AVI, all contain valuable, albeit unstructured data. Streaming sources. Data on the move. In today's fast-paced world, data isn't always sitting still, waiting to be extracted in batches. It can be a continuous flow, often referred to as a stream. Examples: sensor data from smart devices or industrial machinery, website clickstreams, every time you click or scrolls on a web page, social media feeds, live tweets, comments, and financial market data, stock prices changing by the second. This type of data often requires specialized streaming platforms designed to handle high velocity and continuous ingestion with minimal delay. The concept of data quality, the foundation of trust. No matter where data lives or what form it takes, its quality is paramount. Poor data quality is like a chef trying to make gourmet food with rotten ingredients. The end product will be a disaster, or worse, make people sick. Low-quality data can lead to spectacularly bad business decisions, wasted resources, a lack of trust in analytical insights, and frustrated customers. Ensuring high data quality starts even before the transform phase and continues throughout the pipeline. It's an investment in trustworthy decision-making. Key dimensions of data quality include accuracy. Is the data correct and precise? E.g., is the customer's phone number actually theirs, or is it a typo? Completeness. Is all necessary data present? E.g., are there missing values in critical fields like order amount or customer email? Consistency. Is the data uniform across all systems and over time? E.g., is a product ID stored the same way in both the sales system and the inventory system? Is New York always represented as NY or consistently as New York? Timeliness. Is the data up to date and available when needed? E.g., is the inventory count current, reflecting recent sales, or is it from yesterday? Validity. Does the data conform to defined rules and formats? E.g., does a zip code field only contain numbers in the correct format? Is a date of birth within a reasonable range? Key takeaways: the raw materials of insight. Understanding the various types of data and their origins is the critical first step in building effective ETL processes and data pipelines. Recognizing whether data is structured, semi-structured, or unstructured impacts how you plan to extract it, what transformations you'll need to apply, and ultimately, how you can truly derive value from it. Always remember, your downstream insights are only as good as the data that feeds them. In the next chapter, we'll begin our deep dive into the first crucial phase of ETL, extraction, the art of safely gathering data from its origin. Chapter 3. The art of extraction, safely gathering data from its origin. The journey of data begins with its extraction. This is the act of gently, yet effectively, pulling data from its source systems. Imagine yourself as a meticulous archaeologist, carefully excavating valuable artifacts from various different dig sites. You need to know where to look, how to dig without damaging the original site, and how to transport the findings safely for further study. In the world of data, the extract phase of ETL is precisely this critical first step. The first step, getting data out of its silo. Data lives in many different applications and databases, often completely isolated from one another. These isolated pockets of information are commonly called data silos. A sales department might have its customer data in one system, while the marketing department has the same customer's email preferences in another, and the customer support team has their interaction history in a third. The purpose of extraction is to break down these silos and coalesce the data into a central area for processing. The primary goal of extraction is to make a copy of the necessary data without disrupting or degrading the performance of the source system. These source systems are often live, operational applications that businesses rely on constantly. You wouldn't want your data extraction process to slow down customer transactions or prevent an employee from accessing vital information. This makes the safely gathering data aspect incredibly important. Extraction methods, different ways to collect data. The approach to extracting data depends heavily on the source system, the volume of data, and how quickly it needs to be available. Here are some common methods: batch extraction, the scheduled delivery. Concept: this is like a scheduled postal service delivery. Data is collected over a period, e.g., a day, an hour, a week, and then moved all at once in a bulk operation at specific, predefined intervals. How it works: a process runs at a set time, e.g., every night at midnight, to extract a large amount of data that has accumulated since the last run. This might involve querying a database for new customer orders placed that day or downloading all log files from a server. When to use it: ideal for reporting or analytical needs that don't require immediate, up-to-the-second data. It's efficient for large volumes of data that can tolerate some latency. Example: extracting all sales transactions from the previous day's general ledger system to generate daily sales reports for managers. Real-time/streaming extraction, data on the go. Concept: this is like a continuous flow of water through a pipe. Data is extracted almost instantaneously as it is generated, often in very small chunks, called events. How it works: instead of waiting for a batch, individual events are captured as they happen. This might involve listening for specific actions, like a new sensor reading from a machine or a credit card transaction being approved, or continuously reading from a constant data stream. When to use it: critical for scenarios where immediate insights or rapid responses are required, such as fraud detection, live dashboards, or personalized recommendations based on a user's current activity. Example: extracting website click data as a user navigates a site to immediately update their personalized product recommendations or flag unusual activity. API integrations, talking to other systems. Concept: many modern applications provide an application programming interface, API. Think of an API as a set of defined rules and tools that allows one software program to communicate with another in a structured way. It's like a waiter in a restaurant. You tell the waiter what you want, a specific data request, and they go get it for you from the kitchen, the application's underlying database. How it works: your extraction process sends a request to the source system's API, asking for specific data. The API then returns the data, often in a semi-structured format like JSON or XML. This is typically a very controlled and safe way to access data, as the application itself manages what data is exposed and how. When to use it: when source systems offer a well-documented API, providing a clean and controlled way to access data without directly touching their core databases. Common for integrating with third-party software as a service, SaaS applications, e.g., customer relationship management, CRM, platforms, marketing automation tools, payment gateways. Example: using a social media platform's API to extract live audience engagement metrics for a marketing campaign. Database queries and replication, copying the source. Concept: this involves directly querying a database or using its built-in replication features to copy data. How it works: direct querying or database connectors, running specialized commands, often in a language called SQL, directly against the source database to select and retrieve specific tables or columns. This provides granular control over what data is extracted. Change data capture, CDC, a more advanced and highly efficient method that identifies and captures only the changes made to the source database, new rows, updated rows, deleted rows, since the last extraction. This is incredibly efficient, as you're only moving the diff of the data, significantly reducing load on the source system. Database replication, using features of the database itself to continuously copy data from a primary database to a secondary one. The secondary database can then be used as the source for your ETL process, completely offloading the extraction burden from the live operational database. When to use it: when the source is a traditional database and you need efficient, often large-scale, extraction. CDC is particularly useful for minimizing source system impact and transfer volume in scenarios requiring frequent updates. Example: using CDC to capture every new customer sign-up and order from an e-commerce database as they occur, ensuring near real-time updates for a fraud detection system. File parsing, reading documents and logs. Concept: this method is used when data is stored in static files on a server, network share, or cloud storage. How it works: the extraction process reads the files, e.g., CSV, plain text, XML, JSON, or even static Excel sheets, though less ideal for automation, interprets their content according to a predefined structure, and extracts the relevant information. This often involves parsing, which means carefully deconstructing the file to understand its data elements. When to use it: common for ingesting data received from external partners or for processing logs generated by various applications, servers, or networks, where data is simply written to a file. Example: reading daily log files from a web server to extract information about website visitors, pages visited, and any server errors. Challenges of extraction: despite its apparent simplicity, the extraction phase can present several significant hurdles that data professionals must carefully navigate. Source system impact: this is paramount. You must extract data without slowing down or crashing the live operational applications that depend on the source database. Poorly optimized queries, excessive data pulls during peak hours, or inefficient CDC mechanisms can cripple a business's operations. Data volume and velocity: as businesses generate more data, handling the sheer scale, volume, and speed velocity of this new information becomes a constant challenge. Extracting terabytes of data daily or processing thousands of events per second requires robust, carefully designed infrastructure. Security and access: data often contains sensitive information, customer details, financial records, health data. Securely accessing source systems, adhering to strict access controls, who can access what, and encrypting data during transfer are critical to prevent breaches and ensure compliance with data privacy regulations. Data format variations: data from different sources often comes in wildly different formats, character encodings, or structures, even within the same organization. Some fields might be optional in one system and mandatory in another. This diversity makes universal extraction challenging and requires a flexible approach. Schema changes: source systems are not static, they evolve. New fields are added, existing ones are modified, and old ones might be deprecated or removed. An extraction process must be built to be resilient to these changes or must be updated swiftly to avoid breaking the entire data pipeline. An anecdote: the challenge of extracting customer data from legacy systems. A marketing director at a large, established retail chain desperately wanted to personalize promotions for customers. Their customer data, however, was spread across a 20-year-old mainframe system for in-store purchases, a newer cloud-based platform for online sales, and a third-party system for loyalty program signups. Each system had its own unique way of storing customer names, addresses, and purchase dates. The company's initial extraction process was a nightmare. IT staff had to manually run complex, fragile scripts on the mainframe and then export large comma-separated (CSV) files from the other two systems. These files were then haphazardly merged using spreadsheets, a process that was slow, error-prone, and frequently led to duplicate customer records or inconsistent data. The entire process took days, by which time the data was already somewhat outdated. This resulted in frustrated marketers sending irrelevant offers and customers receiving multiple copies of the same email. The solution came with a modern ETL approach. The team implemented an API-driven extraction from the cloud system, the cleanest source, used a changed data capture process for the mainframe to minimize its operational impact, and automated file parsing for the loyalty program. This new, orchestrated pipeline allowed for daily, consistent data extraction, feeding into a comprehensive, golden record customer profile in a central data warehouse. This transformation in the extraction phase alone significantly improved the marketing team's effectiveness, leading to more targeted campaigns and happier customers. Key takeaways: the gateway to data transformation. The extract phase is the crucial first hurdle in any data journey. It demands careful consideration of the source systems, the data volumes and velocity, and the necessary balance between timely data availability and minimizing disruption to live operations. A robust extraction strategy sets the stage for accurate and valuable data transformations, proving that getting the data out is sometimes as challenging and important as what you do with it afterward. With our ingredients safely collected, we're ready to move to the next exciting step: transformation. Chapter 4: Data Alchemy: Cleansing, Structuring, and Enriching Information for Insight. If extraction is like gathering the raw ingredients from various sources, then transformation is where the real culinary artistry begins. This is the T in ETL, and for many data professionals, it's considered the most critical and often the most complex phase. Just as a chef takes raw, diverse ingredients, some dirty, some oddly shaped, some in too large quantities, and turns them into a delicious, cohesive meal, data transformation takes raw, often messy data, and refines it into a clean, structured, and insightful format ready for consumption. Why transform data? The necessity of preparation. The extracted data, fresh from its source system, might be abundant but rarely immediately useful. It's like a chest full of fascinating artifacts that are covered in dirt, some broken, many in strange languages, and all jumbled together. To make them truly valuable for study, you need to clean them, piece them together, translate them, and organize them in a logical manner. The necessity of data transformation boils down to 3 core reasons. Matching business needs. Data extracted from an operational system is optimized for that system's specific function, e.g., processing an order, managing customer support tickets. It's rarely structured perfectly for answering broader business intelligence questions, e.g., what are our total sales trends by regional demographics for the last quarter? Transformation reshapes the data to answer these strategic, often cross-departmental, questions. Improving data quality. As discussed in Chapter 2, raw data often contains errors, inconsistencies, outdated information, or missing pieces. Transformation is the designated phase for improving the accuracy, consistency, completeness, and validity of the data. Without this crucial step, analytical insights will be flawed, leading to poor decisions and a lack of trust in any reports. Optimizing for analysis. Analytical tools and the people who use them, data analysts, data scientists, business users, perform best when data is structured in a clear, consistent, and efficient way. Transformations prepare the data to be quickly queried, easily understood, and efficiently processed, saving analysts time and ensuring reliable results. Common transformations. The Data Artisan's Toolkit. The list of potential transformations is vast, depending on the specific business need and the source data's messiness. However, they generally fall into key categories. 1. Cleansing. The digital deep clean. This is about removing dirt, fixing flaws, and ensuring the trustworthiness of the data. It's often the first step in the transformation journey. Deduplication, identifying and removing duplicate records. Imagine having 3 slightly different entries for John Smith, 123 Main St. One with a typo in the street name, one with a different phone number, one perfect. Deduplication aims to merge these into a single, accurate, and consistent record, so John Smith only appears once. Standardization, ensuring consistency in data formats and values across different sources. Example: standardizing dates, converting 1/15/23, Jan 15, 2023, and 2023 to 1/15, all to a single, consistent format like YYYYMMDD. Example: standardizing state abbreviations, converting CA, Calif, and California all to CA. Example: ensuring product names follow a universal catalog, even if typed differently in local systems. Error correction, fixing obvious errors or invalid entries. This could involve correcting typos, ensuring numbers are within expected ranges, e.g., age cannot be 200, or flagging illogical values that breach business rules. Handling missing values, deciding what to do when crucial data points are absent. Options include deletion, removing records with critical missing data, use with extreme caution as it can lead to data loss. Imputation, filling in missing values with a placeholder, a calculated average, or a predicted value based on other data points, e.g., if a customer's gender is missing, use the most common gender for their age group. Flagging. Simply marking records where data is missing, allowing downstream processes or analysts to handle them appropriately. 2. Structuring and reshaping. Building the right framework. This is about organizing data into a format that makes it easier to analyze, often by combining information from multiple extracted sources. Normalization/denormalization. These are database design strategies. Normalization. Breaking down a large table into smaller, more focused, related tables to reduce data redundancy, storing the same piece of information multiple times, and improve data integrity. For example, instead of repeating a customer's full address in every order they make, store it once in a customer table and link orders to it by a customer ID. Denormalization. Combining data from multiple normalized tables back into a single, wider table specifically for faster data retrieval and query performance, which is often preferred in data warehouses for reporting, even if it introduces some redundancy. Joining data, combining related data from 2 or more different tables or sources based on a common key. This is a fundamental operation in ETL. Example: linking customer purchase data from a sales system with customer demographic data from a CRM using a shared customer ID to get a complete view of purchases by customer type. Aggregation. Summarizing data to a higher level of detail. This involves mathematical operations on groups of data. Example: summing individual sales transactions to get total daily sales or monthly sales by product category. Example: counting the number of unique website visitors per hour. Pivoting/unpivoting, changing the orientation of data. Pivoting, rotating unique values from a row into columns. For example, transforming a list of monthly sales records, each month as a row into a table where each month is a column, showing sales for different products across different months in one row. Unpivoting. The reverse operation, rotating categories from columns into rows, which is often useful for preparing data for specific analytical tools. 3. Enrichment. Adding new value. This involves enhancing the existing data by adding new, valuable information, often from external sources or through calculations based on the existing data. Adding context, external lookups. Geocoding. Converting customer addresses, street, city, state, into precise geographical coordinates, latitude and longitude, to enable map-based analysis and location-based marketing. External data integration. Adding external data like weather information based on a transaction date and location, or demographic data based on a zip code, to provide richer context for analysis. Creating new attributes, calculated fields. Example: calculating a customer's lifetime value from their historical purchases, enabling targeted marketing based on their predicted future spending. Example: deriving a day of the week or hour of the day from a transaction timestamp to analyze time-based trends and peak performance periods. Example: categorizing a customer into a loyalty segment, e.g., bronze, silver, gold, based on their spending, frequency, and recent activity. The garbage in, garbage out principle in action. This old adage is profoundly true in the world of data. All the sophisticated analysis, powerful reports, and cutting-edge machine learning models in the world are meaningless if the data they are based on is flawed. Imagine trying to navigate a city using a map with incorrect street names, missing roads, or outdated landmarks. You'd likely get lost or make bad decisions. The transformation phase is your indispensable opportunity to correct inaccuracies, fill in blanks, ensure consistency, and mold the data into a reliable foundation for all downstream activities. It makes bad data good and good data better. This makes transformation a fundamental investment in trustworthy decision-making and valuable insights. Case study snippet: transforming sales data for regional analysis. A national retail chain wanted to compare sales performance across its different regions. However, the data came from dozens of legacy point-of-sale systems in each individual store, which had evolved independently over years. Initial data problem: store names were inconsistent, e.g., MainCent Store Phoenix, PHNX Main SDR, Phoenix Main Street Store. Product categories were free-form text entered by clerks, e.g., Electronics Division, ELEC. Department: gadgets, Customer loyalty numbers were sometimes missing or entered incorrectly. Sales returns were recorded in a separate system and not linked to original sales transactions. Some sales records had obviously incorrect quantities or prices due to data entry errors or system glitches. Transformation steps applied by the data pipeline. Standardization. All store names were standardized to a central master list and then linked to their specific geographical regions. Product categories were mapped to a controlled, consolidated set of 10 categories, e.g., all variations of electronics became simply electronics. Date formats were unified. Cleansing. Duplicate sales entries were identified and removed. Records with illogical quantities or prices were flagged for review or automatically corrected based on predefined rules. Missing customer loyalty numbers were identified, and attempts were made to fill them in by joining with other customer databases. Invalid loyalty numbers were removed. Joining. Return data was linked to the original sales transactions using a unique transaction ID, allowing for a calculation of net sales, sales minus returns. Aggregation. Individual sales transactions were aggregated to total net sales per store per day, and then further aggregated to total net sales per region per week, providing a clear, summarized view. Enrichment. Geographical coordinates for each store were added from a lookup table, enabling map-based analysis and distance calculations for logistics insights. Result. After these rigorous transformations, the retail chain could finally generate accurate, consistent, and comparable reports comparing regional sales performance. They could identify top and bottom-performing regions, understand product trends at a macro level, and make informed decisions about inventory allocation, marketing strategies, and store expansion. Without the transformation phase, this comparative analysis would have been impossible or highly misleading, leading to poor strategic choices. Key takeaways: turning raw data into gold. Data transformation is where raw information truly becomes valuable. It's an intricate, often challenging, but absolutely essential step in the data pipeline. It ensures that the data is not only accurate and consistent, but also structured optimally to support the analytical and operational needs of the business. Mastering this phase, or at least appreciating its complexity, allows you to recognize an exceptional data product. With our data now cleaned, refined, and reshaped, ready to provide insights, the next crucial step is to put it in its new designated home, the loading phase, which we'll explore next. Chapter 5, the destination line, loading data for analysis and action. After the careful extraction of raw data and its meticulous transformation into a clean, structured, and insightful format, our data journey reaches its final crucial stage. Load. This is the L in ETL, where the refined, high-quality data is delivered to its ultimate destination, ready to be put to work. Imagine a perfectly sorted and labeled package, having traveled through various processing centers, finally arriving at its intended recipient's address. The data is now poised to power reports, dashboards, machine learning models, or even feed back into operational systems. Putting the prepared data to work. The goal of the load phase is simple yet profound: to make the processed data accessible and useful for its intended purpose. Just as a library organizes books for easy retrieval, or a factory stores finished goods for distribution, data needs a well-chosen home that aligns with how it will be consumed. The wrong destination can render even perfectly prepared data difficult to use or slow to access, defeating the purpose of the entire pipeline. Where does data go? Common destination systems. The choice of destination system depends heavily on what you intend to do with the data. Different systems are optimized for different types of consumption and analysis. Data warehouses, the central repository for business intelligence. Imagine a highly organized, specialized library specifically designed for researchers. It contains historical versions of books, meticulously cataloged, cross-referenced, and indexed for speedy retrieval of information relevant to their studies. Characteristics. Data warehouses are optimized for querying and analysis of large volumes of historical data. They typically store structured, aggregated, and highly transformed data based on specific business subjects, e.g., sales, customers, finance. They are designed for read-heavy operations, meaning they are excellent for answering complex business questions, like, what was our sales trend for product X in region Y over the last 5 years? But not for rapid, individual transaction updates. Dimensional modeling. A common way to organize data in a data warehouse is using dimensional models. These consist of fact tables containing numerical measurements or metrics, like individual sales amounts, quantities, or transaction IDs, and dimension tables, providing context and descriptive attributes, like product details, customer information, store locations, or dates. This structure makes analysis intuitive and fast. When to use it? For historical reporting, trend analysis, statutory reporting, business intelligence dashboards, and decision support systems where data consistency and speed of analytical queries are paramount. Data lakes, storing everything, structured or not. Imagine a vast, natural reservoir where water from many sources collects. It can hold raw, untreated water, partially treated water, or even bottled water. It's a place designed to store everything that flows in its original state for future use. Characteristics. Unlike data warehouses, data lakes are designed to store massive amounts of raw data in its native format, regardless of its structure, structured, semi-structured, or unstructured. The idea is to capture data first and worry about specific structuring, schema later, when it's actively needed for analysis. This philosophy is often referred to as schema on read. When to use it? For big data analytics, machine learning, data science exploration, and when you're not sure how you'll use the data up front, allowing for maximum flexibility. They are commonly built on distributed file systems in the cloud, e.g., Amazon S3, Azure Data Lake Storage, Google Cloud Storage. Key insight: data lakes are about storage flexibility and raw data access, enabling a wider variety of analytics than traditional warehouses. They often serve as the initial landing zone for data, a common destination in an ELT pattern, which we touched upon in Chapter 1, becoming the source for data warehouses, where selected data is then further refined. Operational databases, back to the application world. Imagine a daily ledger for a small business. Transactions are recorded continuously to keep track of current operations. Or an inventory system that needs to know exactly how many units of a product are currently in stock. Characteristics. Sometimes, the transformed data needs to be loaded back into a system that applications use directly. This might be to update customer profiles in a customer relationship management (CRM) system, synchronize inventory across multiple systems, or feed a fraud detection system with enriched transaction data that needs to be part of the live operational flow. These are typically transactional databases optimized for frequent, small, real-time updates. When to use it? When immediate, updated operational data is required by an application to function correctly. This is less common for pure analytical ETL, but vital for certain operational use cases. Reporting tools and dashboards, direct consumption. Imagine a TV screen displaying a real-time stock market ticker or a scoreboard at a sports game. Characteristics. In simpler scenarios, processed data might be loaded directly into specialized tools that generate visual reports, interactive dashboards, or business intelligence visualizations. While these tools don't store vast amounts of historical data themselves in the same way a data warehouse does, they are the immediate consumption point for the end user. When to use it? For immediate visualization and monitoring of key performance indicators. KPIs, though the underlying data usually still lives in a database, data warehouse, or data lake that the tool connects to. In some cases, for very small datasets or specific live monitoring, data might be loaded directly into the visualization tool's quick access memory. Loading strategies. How data is loaded can significantly impact performance, data consistency, and the user experience. Choosing the right strategy is crucial. Full load, replacing everything. Concept: this is like emptying out an entire archive and replacing it with a completely new one every time the load process runs. All existing data in the target system is deleted and then replaced with the fresh, transformed dataset. When to use it? For smaller datasets, or when you need absolute certainty that the target system perfectly mirrors the latest source data, without any old or stale records. It's conceptually simpler to implement, but can be resource-intensive and slow for large volumes of data. Incremental load, adding updating new data only. Concept, this is like simply adding new letters to a mailbox, or only updating the specific pages in a book that have changed, leaving the rest untouched. Only new or changed records, since the last load, are added or updated in the target system. When to use it? For large datasets where full loads are impractical due to time or resource constraints, or when you need data to be updated frequently without recreating the entire dataset. This requires a mechanism to identify new or changed records, such as unique identifiers, last modified timestamps, or change data capture, CDC logs from the source. This is the most common and efficient loading strategy for many analytical pipelines. Streaming load, continuous updates. Concept, this is like a continuous news ticker, constantly displaying new headlines as they break. Data is loaded and updated in real time as it arrives, usually in very small, continuous chunks. When to use it? For use cases requiring extreme timeliness and immediate reaction, such as real-time fraud detection, live gaming leaderboards, or immediate customer behavioral analysis. This often leverages specialized streaming platforms and databases optimized for high-velocity inserts. Considerations for loading. Even with the right destination and strategy, several factors need careful management during the load phase. Performance, loading large volumes of data quickly and efficiently is paramount. Poorly optimized loads can impact the performance of the target system, especially if it's being actively queried by users or other applications. Careful indexing in databases or efficient file formats in data lakes are key. Data consistency and integrity, ensuring that the loaded data remains accurate and isn't corrupted during the transfer is vital. It's crucial that all data intended to be part of a single logical update either succeeds completely or fails completely, to prevent partial or inconsistent data. Database transactions, all-or-nothing operations, are often used to ensure data integrity during loading. Scalability. The loading process must be able to handle increasing data volumes and velocity as the business grows. This often means leveraging distributed loading technologies that can spread the workload across multiple servers. Auditing and lineage. It's often critical to know what data was loaded, when, and from where. Data lineage tracks the data's journey, from source to destination, including all transformations applied. This is vital for debugging issues, ensuring regulatory compliance, and fostering trust in data's origins and transformations. An analogy, the library versus the filing cabinet, different destinations for different needs. Imagine you're collecting information for various purposes. If you're writing a detailed research paper, like complex business analysis, you'd send your collected, meticulously organized, and verified notes to a well-structured library, the data warehouse. It's designed for deep, historical research, easy cross-referencing, and multiple people can access it efficiently for specific topics. If you're just keeping all your raw receipts, notes, and documents for future reference, without immediate organization, you might just dump them into a digital filing cabinet or a spacious attic, the data lake. You know they're there, and you can sort through them later if needed, but they aren't immediately organized for specific queries. If you're updating a single customer's contact details in a live system, an operational update, you'd put the new information directly into their specific folder in an active filing system, an operational database, not the main archive or the big everything box. Each destination serves a unique purpose, and choosing the right one is key to maximizing the value of your process data. Key takeaways: delivering data to drive decisions. The load phase is the culmination of all the efforts in extraction and transformation. It's where the cleaned and structured data is finally made available for consumption, driving business intelligence, analytics, and operational processes. Choosing the correct destination and loading strategy is vital for optimizing performance, ensuring data integrity, and ultimately empowering data-driven decision-making. With our data now residing in its new home, the next logical step is to understand how we can make this entire flow automated and reliable. Which brings us to the broader topic of building robust and automated data pipelines. Chapter 6, Orchestrating the Flow. building robust and automated data pipelines. We've now explored the three foundational stages: extract, transform, and load. Individually, these are powerful steps, turning raw data into something useful. However, in the real world, data doesn't just perform a one-off ETL dance. It needs to flow continuously, reliably, and automatically. This is where the concept of a data pipeline moves beyond just the ETL acronym and into a comprehensive, automated system for data delivery. Think of a modern manufacturing assembly line. Raw materials come in, pass through various stations where they are shaped, assembled, and quality checked, and finally, a finished product rolls off at the end. This entire process is automated, synchronized, and constantly monitored. A data pipeline is precisely this for information: an automated, end-to-end system that reliably moves and processes data from its origin to its destination. Beyond one-off ETL, the need for automation. In the early days, ETL might have involved manual scripts or nightly jobs that ran in isolation. An analyst might manually trigger a process to update a particular report. But as data volumes grew and the need for fresh insights became more pressing, manual interventions became a bottleneck and a source of errors. The business needed data that was not just right, but also ready, consistently available, and up-to-date. This pushed the evolution from discrete, often manual, ETL tasks to integrated, automated data pipelines. What makes a pipeline robust? A robust data pipeline isn't just a series of steps chained together. It possesses several key characteristics that ensure its reliability, efficiency, and ability to handle unexpected situations gracefully. Automation, the heartbeat of the pipeline. Concept: this is the cornerstone. Once set up, a pipeline should run with minimal human intervention. It should automatically trigger, execute its tasks, and handle common scenarios. Why it's important? Automation frees up valuable data professionals to focus on designing new solutions and extracting deeper insights, rather than manually running or babysitting existing data flows. It reduces the chance of human error and ensures consistency. Scheduling, the pipeline's clock. Concept: pipelines need to run at specific times or predefined intervals. This could be hourly, nightly, weekly, or even continuously for real-time data. Why it's important? A scheduler is the alarm clock or timer that tells the pipeline when to start. It ensures data is refreshed exactly when it's needed, providing timely insights without manual triggers. Dependencies, ensuring the right order. Concept: many pipeline steps are dependent on others. You can't transform data until it's been extracted, and you can't load it until it's transformed. Further, one pipeline might depend on the successful completion of another. Why it's important? A robust pipeline system understands and manages these dependencies. It ensures tasks execute in the correct order, prevents downstream tasks from starting if an upstream one has failed, and can even allow independent tasks to run concurrently, speeding up the overall process. Error handling and retries. What happens when things go wrong? Concept: despite best efforts, things will go wrong. A network glitch, a source system temporarily unavailable, or an unexpected data format can cause a pipeline step to fail. Why it's important? A robust pipeline has built-in mechanisms to handle errors gracefully, log the error, notify relevant personnel, e.g., via email or a message to a team chat. Retry. Attempt to rerun a failed step a few times before giving up, as many temporary issues resolve themselves. Quarantine bad data. Isolate problematic records rather than letting them corrupt the entire dataset or causing the whole pipeline to stop. Idempotency, running multiple times safely. Concept: this is a sophisticated term for a simple but powerful concept. Performing an operation multiple times should have the same effect as performing it once. For example, if your loading step attempts to add the same record twice, an idempotent design ensures it's only added once, or merely updated if it already exists, rather than creating duplicates. Why it's important? This is crucial for handling retries safely. If a job fails halfway through and then retries from the beginning, you don't want to double process data that was successfully handled the first time. Key components of a data pipeline. While a pipeline can be built from many tools, some general components are essential for its operation. Schedulers, orchestrators, the conductors of the orchestra. These are the tools or systems responsible for defining, scheduling, monitoring, and managing the execution of tasks within your pipeline. They know the dependencies between steps and ensure everything runs in the right order and at the right time. They also handle error notifications and retries, acting as the central control panel for your data flows. Analogy: the project manager who ensures all tasks are completed in order, notifies the team of any blockers, and reschedules if necessary. Data connectors, the bridges between systems. These are the specific pieces of software or configurations that enable the pipeline to communicate with various data sources and destinations. They understand how to speak the language of different databases, APIs, file systems, and cloud services to extract or load data. Without them, your pipeline would be isolated islands. Analogy: the universal adapters and cables that allow your electronic devices to plug into different sockets or ports. Processing engines, the engines of transformation. These are the underlying computational powerhouses that execute the actual data transformations. They might be specialized software frameworks designed for large-scale data processing, like those discussed in Chapter 7, or simply the compute resources running your custom scripts, as mentioned in Chapter 4. They are the muscle that does the heavy lifting of joining, cleansing, and aggregating data. Analogy: the various machines in a factory assembly line the lathes, saws, welding robots, each performing a specific task to shape the raw materials into finished parts. The benefits of a well-designed pipeline: speed, reliability, cost efficiency. Implementing robust data pipelines yields significant advantages for any organization. Speed. Automated pipelines deliver data much faster than manual processes, leading to quick insights and accelerated decision-making. In a competitive landscape, the rapid availability of fresh, accurate data is often a differentiating factor. Reliability. By automating processes and building in robust error handling, pipelines ensure that data is consistently available and accurate, significantly reducing the risk of human error and data quality issues, which we know from Chapters 2 and 4 can be very costly. Cost efficiency. Automation reduces the need for constant manual intervention, freeing up valuable human resources for more strategic, analytical, and design-oriented work rather than repetitive tasks. It also helps optimize compute resources, as tasks run only when needed. Scalability. Pipelines designed with scalability in mind can handle increasing volumes, velocity, and variety of data without requiring a complete re-architecture. This is vital as businesses grow and data generated from new sources, like IoT devices or social media, explodes. Consistency. By enforcing standard procedures for data movement and transformation, pipelines ensure that everyone in the organization is working with the same, consistent view of the data. This eliminates confusion and conflicting reports that arise from different departments using slightly different data versions. Case story: automating daily sales reports with a pipeline. A small but rapidly growing e-commerce business relied heavily on daily sales reports to adjust marketing campaigns, manage inventory, and project revenue. Initially, the process was mostly manual and created significant bottlenecks. A data analyst would manually download daily sales data from the e-commerce platform into a spreadsheet (CSV) file each morning. They would then manually download customer loyalty points data from a separate rewards program system. The analyst would open both files in a spreadsheet program, manually copy-paste, and use complex formulas like VLOOKUP to combine sales information with loyalty data. After combining, they would manually summarize sales by product category and region, checking for obvious errors. Finally, they would create a simple report and email it to the management team. This entire manual process took 2 to 3 hours every day, was prone to human errors, and if the analyst was sick or on vacation, the critical report would be delayed or simply not generated. To streamline this, they built a simple data pipeline. Extraction. Automated scripts were set up to use the e-commerce platform's API to pull sales data and the loyalty program's API to pull points data, storing them in a temporary location. Transformation. A transformation script automatically joined the two datasets based on a common customer ID, calculated daily net sales totals by product and region, and applied a basic data quality check to flag any records with missing essential data. Loading. The prepared, clean data was then automatically loaded into a cloud-based data warehouse, ready for consumption. Orchestration. A simple scheduler was set to run this entire sequence starting at 4 a.m. every day. The orchestrator ensured data was extracted first, then transformed, and finally loaded. If any step failed, e.g., the e-commerce API was temporarily down, an error alert was automatically sent to the analyst's team, allowing them to intervene quickly. Outcome: the daily sales report was now automatically generated and available to management by 6 a.m. every day, consistent and accurate. The data analyst's time was freed up for deeper strategic analysis rather than repetitive manual work. The business could react faster to current sales trends, and their decisions were based on far more reliable and timely information. Key takeaways: from manual steps to automated efficiency, data pipelines are the backbone of modern, data-driven organizations. They go beyond mere ETL, building automated, robust, and intelligent systems that consistently deliver high-quality data. Understanding how these pipelines are constructed and orchestrated is crucial because they are what truly unlocks the continuous flow of valuable information. In our next chapter, we'll explore some of the categories of tools and technologies that data professionals use to build and manage these powerful data highways, bringing these concepts to life with real-world examples. Chapter 7. The Data Artisan's Toolkit, exploring technologies for ETL and pipelines. You now understand what ETL is and how data pipelines allow it to flow seamlessly and automatically. But how are these sophisticated processes actually built and managed in a real-world setting? Just as a builder uses various tools, a hammer for nails, a saw for wood, a drill for holes for different tasks, data professionals employ a diverse set of technologies to extract, transform, load, and orchestrate data. It's important to remember that there's no single magic button solution that fits all needs. The choice of tools depends on many factors: the size and complexity of your data, how quickly it needs to be processed, your budget, your team's existing skills, whether you operate on your own servers or in the cloud, and the specific requirements of your business. This chapter will provide a high-level overview of the major categories of tools you might encounter. Our focus remains on the function these tools provide and the types of problems they solve, rather than diving into intricate technical details or specific coding examples. This approach ensures accessibility for both print and audio formats. Categorizing the tools, a functional overview. We can broadly categorize data pipeline tools based on their primary function and general approach. Scripting languages, the flexible DIY approach. Concept. These are general-purpose computer programming languages that are widely used for data manipulation due to their versatility and rich ecosystems of specialized libraries. They offer the highest degree of control and customization. How they work. Data professionals write custom code to perform every step, making connections and extracting data, e.g., calling an API or querying a database, performing complex transformations, e.g., cleaning text, doing calculations, joining datasets, and ultimately loading the prepared data into its destination. Pros: highly flexible, cost-effective, many are open source and free to use, allows for extreme customization to unique data problems, well-suited for unique, complex, or rapidly changing transformation logic. Cons: requires technical programming skills to develop and maintain, can become complex to manage, debug, and scale for very large or numerous pipelines if not properly organized. Maintenance relies heavily on the quality of the written code. Common examples: Python, a favorite due to its readability and powerful libraries like pandas for data manipulation, requests for handling web data, and SQL Alchemy for database interactions. SQL, primarily for querying relational databases for both extraction and in database transformation. Java, and are often used for statistical analysis and data visualization, but also capable of ETL. ETL platforms, graphical tools, drag-and-drop power. Concept: these are specialized software applications designed specifically for ETL tasks. They aim to simplify the process by often providing a visual drag-and-drop interface, a GUI or graphical user interface, to design data flows, reducing the need for extensive manual coding. How they work: users visually build data pipelines by connecting pre-built components, e.g., a database connector icon plugged into a filter data icon, which then leads to a join tables icon, and finally a load to data warehouse icon on a canvas. The tool translates these visual workflows into executable code behind the scenes. Pros: faster development for many standard ETL tasks, often requires less deep coding expertise for initial setup, includes built-in features for metadata management, data about data, scheduling, and sometimes basic error handling. Good for complex projects across large teams, as the visual representation can be easier to share and discuss. Cons: can be expensive due to licensing costs, as many are proprietary software, may be less flexible or require workarounds for highly custom or cutting-edge transformation logic compared to scripting. Can still have a steep learning curve for the tool itself and its specific way of doing things. Common examples: Informatica Power Center, Talend Open Studio Data Integration, Microsoft SQL Server Integration Services, SSIS, Oracle Data Integrator, IBM Data Stage. Cloud-native services: the managed solution. Concept: these are services offered by major cloud providers, like Amazon Web Services, Microsoft Azure, Google Cloud Platform, that are specifically designed for ETL and data pipeline tasks. They are often serverless, meaning you don't manage the underlying physical servers or infrastructure. The cloud provider handles it all. How they work: you configure your data sources, transformations, and destinations within the cloud platform's web-based interface or through code. The cloud service automatically scales the computing resources up or down as needed to run your pipeline based on the data volume and processing requirements. They integrate seamlessly with other services within the same cloud ecosystem. Pros: highly scalable, can handle massive peaks in data volume without manual intervention. Often cost-effective due to a pay-as-you-go pricing model. Greatly reduces the burden of infrastructure management for your team, offers excellent integration with other cloud-based data storage and analytical services. Cons: can lead to vendor lock-in, making it harder to move your pipelines to another cloud provider or back to your own on-premises servers. Requires learning cloud-specific concepts and terminology, which can introduce a new layer of complexity. Common examples: AWS Glue, Amazon Web Services, Azure Data Factory, Microsoft Azure, and Google Cloud Dataflow, based on Apache Beam, a versatile big data processing framework from Google Cloud. Orchestration workflow management tools, the schedulers and conductors. Concept: while some ETL platforms have built-in schedulers, dedicated orchestration tools specialize in defining, scheduling, monitoring, and managing complex sequences of tasks, including your ETL jobs, but also other scripts, machine learning model training, or report generation. They are the control tower for your entire data ecosystem. How they work: you define your data pipeline as a series of interdependent tasks, often visualized as a directed acyclic graph, DAG, which outlines the order and relationships of operations. The orchestrator ensures these tasks execute in the correct order, handles retries for failed tasks, and surfaces errors or provides status updates through dashboards. Pros: centralized control and monitoring for all data-related tasks, robust error handling and retry mechanisms, typically open source with strong community support, which means extensive documentation and online help. They provide a single pane of glass for seeing the status of all your data jobs. Cons: can be complex to set up and manage initially, especially for larger infrastructures. Often requires some scripting knowledge to define tasks and workflows. Common examples: Apache Airflow, a widely adopted open-source platform for programmatically authoring, scheduling, and monitoring workflows, Prefect and Dagster. Streaming platforms, real-time processing powerhouses. Concept: These are highly specialized technologies designed to handle data that arrives in continuous, high-velocity streams, enabling real-time or near real-time ETL. They contrast with traditional batch processing by processing data event by event as it flows. How they work: they capture incoming data events, e.g., a website click, a sensor reading, a financial trade, as they happen. They then immediately process these events incrementally, often performing immediate transformations before loading them to a real-time destination or another subsequent stream for further processing. Pros: enables immediate insights and rapid reactions, crucial for applications like fraud detection, live dashboards, instant personalized recommendations, or immediate responses to IoT sensor data. Cons: more complex to design, implement, and maintain than traditional batch processing, as they require careful consideration of event ordering, exactly once processing, and managing continuous flows of data. Requires different architectural considerations. Common examples: Apache Kafka, a distributed streaming platform that acts as a central hub for collecting and publishing data streams; Apache Flink, a powerful stream processing engine; and Apache Spark Streaming, a module within the Spark Analytics engine for real-time data processing. Choosing the right tool, factors to consider. With so many options, how do organizations pick the right tools for their data pipelines? It's almost always a combination of several factors: data volume and velocity. Small, static datasets might be fine with simple scripts. Huge, high-velocity, real-time data demands cloud services or specialized streaming platforms. Budget: proprietary ETL platforms can involve significant licensing costs. Open-source solutions are free, but often require more internal expertise for setup and maintenance. Cloud services operate on a pay-as-you-go model. Team expertise: does your team have strong programming skills? Are they already familiar with specific cloud environments? The existing skill set often influences the initial choice. Existing infrastructure: what databases and systems are already in place? Compatibility and seamless integration with existing data sources and destinations are key. Regulatory compliance and security: certain industries have strict requirements for data handling, storage, and auditing, which might influence tool choice, e.g., requiring specific encryption, strict access controls, or on-premises solutions. Time to market: how quickly do you need to get the pipeline up and running? Visual tools or managed cloud services can often accelerate initial development time compared to custom code. Key takeaways: many roads lead to flowing data. The world of ETL and data pipeline tools is rich, diverse, and constantly evolving. There's no single best tool, but rather a spectrum of options, each with strengths and weaknesses that make it suitable for different scenarios. Understanding these categories allows you to appreciate the diverse technical capabilities required to manage the flow of data within any organization. Data professionals, much like skilled artisans, select the right tools from their diverse toolkit to sculpt, refine, and deliver the invaluable product that is clean, ready-to-use data. In the next chapter, we'll shift our focus from the what and how to the how to do it well, discussing best practices and design principles that ensure your data workflows are not just functional, but exemplary. Chapter 8. Crafting Excellence: Best Practices and Design Patterns for Data Workflows. Building a functional data pipeline is one thing. Building a truly great one is another. Just as an architect designs a building not just to stand, but to be safe, efficient, and aesthetically pleasing, data engineers apply best practices and design patterns to create data pipelines that are not only effective, but also robust, scalable, maintainable, and secure. This chapter delves into the principles that elevate a simple data movement process into an exemplary data workflow. Principles for robust design. These are foundational guidelines that guide the design and implementation of any successful data pipeline. They ensure that your data infrastructure is a long-term asset, not a source of constant headaches. Modularity: breaking down complex tasks. Concept: instead of creating one giant, monolithic pipeline that tries to do everything from extraction to loading in a single, unbroken sequence, break it down into smaller, independent, self-contained components or modules. Each module should have a clear, single responsibility, e.g., one module specifically for extracting customer data, another for transforming order data, a third for loading aggregated sales figures. Why it's important. Easier debugging. If something breaks, you can pinpoint the problematic module quickly, avoiding a frantic search through a complex, intertwined system. Reusability. A module that extracts customer data can be reused across multiple different pipelines that need that same customer information, saving time and ensuring consistency. Maintainability. Small modules are easier to understand, modify, and update without affecting the entire system. This means less risk when making changes. Parallel processing. Independent modules can often run concurrently, speeding up the overall pipeline execution time. Analogy. Instead of baking one giant cake from scratch in a single, complicated recipe, prepare different elements separately, say, a cake batter module, a frosting module, and a decorative module. Each can be perfected independently and then assembled. Scalability. Growing with your data needs. Concept. Design your pipelines so they can gracefully handle increasing volumes, velocities, and varieties of data without requiring a complete re-architecture. An initially small amount of data can rapidly grow as a business expands or new data sources emerge. Why it's important. Prevents pipelines from becoming bottlenecks as your business grows. It ensures that your data systems can expand capacity, e.g., by adding more processing power or storage instead of being constrained by fixed, rigid limits. How to achieve it. Use technologies designed for distributed processing, where work is spread across multiple machines. Leverage cloud solutions with auto-scaling capabilities, which automatically adjust resources based on demand, and design for parallel execution of tasks wherever possible. Observability, knowing what your pipeline is doing. Concept, build your pipelines with introspection. This means creating them in a way that their internal state, health, and performance are easily understandable and visible at all times. This includes comprehensive logging, detailed metrics, and clear monitoring dashboards. Why it's important. You need to know if a pipeline is running, if it's succeeding or failing, how long each step is taking, and if the data quality is as expected. This allows for proactive identification of issues, rather than waiting for an end user to complain that a report is missing or incorrect. It facilitates problem solving. How to achieve it. Implement comprehensive logging, recording events, warnings, and errors. Metrics, tracking performance indicators like processing time, data volume processed per minute, number of records affected, and automated alerts, notifying you immediately of failures, significant delays, or anomalies. Resilience, handling failures gracefully. Concept, design pipelines to be robust against failures. Assume that network issues, temporary source system outages, unexpected data formats, or system glitches will occur. Your pipeline shouldn't collapse at the first sign of trouble. Why it's important. Minimizes downtime and data loss. Allows the pipeline to recover automatically or with minimal manual intervention, ensuring continuous data flow even in the face of minor disruptions. How to achieve it. Implement retry mechanisms for temporary failures, e.g., trying to connect to a database a few times before giving up. Robust error handling logic, e.g., identifying and quarantining problematic records instead of stopping the entire process. And fault-tolerant architectures where possible, e.g., redundant systems that can take over if one fails. Security, protecting sensitive information. Concept, embed security considerations at every stage of the pipeline, from when data is extracted until it is loaded and stored. Why it's important. Protects sensitive business and customer data from unauthorized access, modification, or exposure. Ensures compliance with increasingly strict data privacy regulations, e.g., GDPR in Europe, CCPA in California. A data breach can have devastating financial and reputational consequences. How to achieve it. Use secure connections, encryption during data transfer. Implement strict access controls, who can access which data and with what permissions. Encrypt data at rest, when it's stored, anonymize or mask sensitive data, like personally identifiable information, when it's not strictly needed for analytical purposes, and conduct regular security audits of your pipelines. Data governance and stewardship, who owns the data, It's not enough to build a technically sound pipeline. You also need clear rules and responsibilities for the data it handles. This is where data governance comes in. Data governance. This is the overall framework of policies, procedures, roles, and technologies that ensures data is managed as a strategic asset within an organization. It defines who is responsible for data quality, security, privacy, and approved usage. Think of it as the comprehensive rulebook for data. Data stewardship. This is the practical implementation of data governance. Data stewards are individuals or teams, often within specific business units, who are responsible for the well-being of specific datasets. They ensure data quality, understand data lineage, where data came from and how it was transformed, help resolve data issues, and act as subject matter experts for their data domains. Importance of data documentation and metadata. Documentation. Clear written explanations of what each pipeline does, its inputs, outputs, and any transformations applied. This is invaluable knowledge for current and future team members. Metadata, often described as data about data. This includes structural information, e.g., column names, data types, operational details, e.g., when a pipeline last ran, how many rows it processed, and business context, e.g., what a specific data field means, who owns it, what its quality is. Metadata is essential for understanding, trusting, and governing data effectively. Data lineage, the ability to trace data from its ultimate origin through all transformations, consolidations, and loads to its final destination, e.g., a report or dashboard. This is crucial for auditing, debugging. If a number in a report seems off, you can trace it back, and understanding the reliability of any analytical output. Testing your data pipelines. Ensuring accuracy. Like any software system, data pipelines must be rigorously tested. Without testing, you cannot guarantee the reliability or accuracy of the data they produce. Why testing is crucial. Prevents bad data. Catches errors and inconsistencies before they contaminate downstream systems and reports, preventing costly mistakes. Ensures correctness. Verifies that transformations are applied as expected and that the data adheres to business rules and quality standards. Validates performance. Checks if the pipeline runs efficiently and within acceptable timeframes, especially as data volumes grow. Handles edge cases. Ensures the pipeline can handle unexpected data, missing values, or unusual scenarios without breaking. Types of testing. Unit tests. Testing individual components or transformation functions in isolation, ensuring they perform their specific task correctly. Integration tests. Testing how different components of the pipeline, e.g., an extraction module connected to a transformation module, work together seamlessly. Data quality tests. Specific checks, often automated, to ensure the accuracy, completeness, consistency, and validity of the data after transformation, before it's loaded to its final destination. Performance tests. Measuring how fast the pipeline processes data under various loads and conditions to identify bottlenecks. End-to-end tests. Running the entire pipeline from source to destination and verifying the final output against expected results. Collaboration. Data engineering is a team sport. Building and maintaining robust data pipelines is rarely a solo endeavor, especially in larger organizations. It requires close collaboration and clear communication between various roles. Data engineers design, build, and maintain the actual pipelines and the underlying data infrastructure. Data analysts and scientists, the primary consumers of the data, providing requirements for data transformation, validating data quality, and understanding its nuances for their analytical work. Business stakeholders, the business leaders and users who define the problems to be solved, the data insights they need, and the ultimate value the data provides. Source system owners, the teams or individuals who manage the original systems where data resides. They provide crucial context about the source data's structure, meaning, and limitations. Effective communication, a shared understanding of data definitions, and clear expectations for data quality are vital for success. Key takeaways: building for the long term. Crafting excellence in data workflows means moving beyond just making things work. It involves a systematic, thoughtful approach that prioritizes modularity, scalability, observability, resilience, and security. It means embracing data governance, rigorously testing, and fostering strong collaboration across teams. By adopting these best practices and design patterns, you build not just data pipelines, but reliable, trustworthy, and enduring data assets that truly empower an organization's future. With reliable pipelines in place, the next crucial step is keeping them running smoothly and efficiently, which brings us to the operational reality of monitoring, maintenance, and troubleshooting. Chapter 9: The Data Flow's Pulse. Monitoring, maintenance, and troubleshooting. Imagine a complex factory running 24/7, producing vital goods. Would you simply set it up and walk away, hoping for the best? Of course not. You'd have control panels displaying key metrics, sensors detecting anomalies, and a team constantly monitoring its operations, performing scheduled maintenance, and jumping in immediately if something goes wrong. Data pipelines are no different. They are living, breathing systems that require continuous attention to ensure they are performing as expected, delivering high-quality data, and responding effectively to issues. This chapter focuses on the operational aspect of data pipelines, how to monitor their health, maintain their efficiency, and troubleshoot when the flow inevitably encounters a blockage. Why monitor? Staying ahead of problems. Monitoring is about keeping a vigilant eye on your data pipelines to detect issues before they become critical or even catastrophic. Just like a doctor monitors a patient's vital signs, proactive monitoring prevents unpleasant surprises and ensures consistent, reliable data delivery. Performance monitoring. Is it running fast enough? What to monitor? How long ETL jobs take to complete their runtime, the volume of data processed, e.g., number of rows, gigabytes, the computing resources consumed, CPU usage, memory, network bandwidth, and the speed of data transfer between different system components. Why it's important. Slow pipelines can delay critical business reports, hinder real-time applications, and cost more in computing resources. Performance monitoring helps identify bottlenecks, specific parts of the pipeline that are slowing things down, and allows you to optimize your processes for speed and cost efficiency. Example: a daily sales report pipeline that typically takes 30 minutes suddenly starts taking 2 hours. This indicates a performance issue that needs investigation, perhaps a growing data volume exceeding capacity. Data quality monitoring. Is the data still good? What to monitor? Checks for anomalies, deviations from expected patterns, or breaches of data quality rules, as discussed in Chapter 4. This includes looking for sudden drops or spikes in record counts, unexpected null or empty values in critical fields, invalid data formats, or numerical values that are out of an acceptable range. Why it's important. Even if the pipeline itself runs successfully without crashing, the data it produces could still be flawed. Data quality monitoring acts as a final checkpoint, ensuring the output is trustworthy before it reaches business users. Example: suddenly, 20% of customer phone numbers are missing in the loaded data, or the total sales figure for a day is unusually high or low without a corresponding business event. Error alerts. Knowing when things break. What to monitor. Any failure in a pipeline step, connectivity issues to source or destination systems, resource exhaustion, e.g., disk storage reaches capacity, or security breaches, e.g., unauthorized access attempts. Why it's important. Immediate notification of failures is crucial for rapid response. The faster you know about a problem, the faster you can fix it, minimizing its impact on downstream systems, business operations, or revenue. Example: an email or a message to a team chat for ETL job failed to connect to CRM database, or transformation step terminated unexpectedly due to data type mismatch. Logging and auditing. The pipeline's diary. Just like a black box in an airplane records flight data, good data pipelines keep detailed logs. These logs are invaluable for understanding what happened, when, and why, providing a comprehensive historical record. What to log. Start and end times of each job step, essential for performance analysis and identifying delays. Number of records processed, for volume tracking, reconciliation, and data quality checks. Details of any errors or warnings, crucial for immediate troubleshooting. they contain the specific messages indicating what went wrong. Configuration settings used for each run helps reproduce issues and ensures consistent execution. User actions for manual operations, for auditing and security purposes, showing who initiated what process. Traceability and auditing. Comprehensive logging contributes directly to data lineage, discussed in Chapter 8, allowing you to trace any piece of data from its final destination back to its original source, through all transformations it underwent. This is vital not just for debugging, but also for regulatory compliance, proving data integrity for auditors and fostering trust in your data assets by demonstrating transparency. Auditing. Logs provide a record of all activities, demonstrating adherence to data handling policies, security protocols, and who accessed what data when. Troubleshooting common issues. Despite best efforts in design and monitoring, issues will inevitably arise. Being able to effectively troubleshoot is a key skill for anyone involved with data pipelines. Understanding common failure points can significantly speed up resolution. Connectivity problems, the broken bridge. Symptom: the pipeline fails at the extract phase, cannot connect to source, or load phase, cannot connect to destination, often displaying messages about network issues, timeouts, or authentication errors. Investigation. Check network connection between the pipeline server and the source destination database. Firewall rules that might be blocking traffic. Verify the status of the database server itself. And importantly, ensure the credentials, username, password, API keys, and permissions used by the pipeline are correct and haven't expired. Data format mismatches, the unexpected ingredient. Symptom: a transformation step fails, citing errors like invalid data type, cannot convert text to number, or unexpected characters appear in the data. Investigation. The most common culprit is that the source system has changed its data format, meaning its schema has shifted, or a new, unexpected type of data has appeared that the transformation logic wasn't designed to handle. Inspect the raw source data, if possible, and the error message to pinpoint the exact data element causing the issue. This often requires close collaboration with the source system owners. Performance bottlenecks, the slow conveyor belt. Symptom: the pipeline runs much slower than usual, or certain individual steps take an unusually long time to complete, causing delays in overall data delivery. Investigation. Check resource usage, CPU, memory, disk I/O on the servers or cloud instances running the pipeline. Look for slow queries in the extraction phase, inefficient transformation logic, e.g., complex joins on huge datasets might need optimization, or slow write operations to the destination, where the loading process is taking too long. Resource exhaustion, the overloaded truck. Symptom: the pipeline crashes or fails due to out-of-memory errors, disk full messages, or hitting limits on CPU or network resources. Investigation. The volume of data might have increased unexpectedly, or the processing engine needs more allocated resources. This might require scaling up the compute power, e.g., assigning a larger server, optimizing the processing logic to use less memory disk, or implementing strategies to process data in smaller chunks. Maintaining your pipelines, regular checkups and updates. Successful pipelines aren't set-it-and-forget-it systems. They require ongoing care, much like a well-oiled machine needs regular servicing. Regular review. Periodically review pipeline performance, analyze logs and error trends to identify areas for optimization, or spot potential future problems before they escalate. This could involve weekly or monthly review meetings. Updates and upgrades. Keep the underlying software, libraries, and tools used by your pipelines updated. This is crucial for leveraging new features, applying security patches, and benefiting from performance improvements. Ignoring updates can lead to vulnerabilities or compatibility issues. Documentation updates. As pipelines evolve, change, or new insights are gained, ensure your internal documentation is current. Accurate documentation is crucial for new team members getting up to speed and for experienced members efficiently troubleshooting or modifying pipelines. Refactoring. As business needs change or new data sources or technologies emerge, parts of the pipeline might need to be re-engineered, a process called refactoring for better efficiency, accuracy, or to integrate with new systems. Case story: diagnosing a stalled river in a retail data pipeline. A large online retailer's crucial daily sales dashboard suddenly stopped updating. The last successful update showed data from 2 days prior. Management quickly noticed, as they relied on it heavily for inventory decisions for popular, fast-moving items like back-to-school supplies. The data engineering team's monitoring system immediately alerted them to the pipeline's failure. Checking the logs for the specific sales dashboard pipeline, they found a recurring error message. Failed to connect to source database. Connection refused. Troubleshooting steps, connectivity check. They first confirmed that the source database server itself was online and accessible from other tools and applications. It was. Credential check. They verified that the specific database user account and password used by the pipeline were correct and hadn't expired. These were also fine. Firewall network rules. A quick investigation revealed that the IT operations team had implemented a new firewall rule overnight to block certain types of outbound network traffic for security reasons. Unfortunately, and unintentionally, this new rule was inadvertently blocking the pipeline server from establishing a connection to the database server. Resolution. Once the new firewall rule was adjusted to explicitly allow the necessary connection from the pipeline server to the database, the pipeline successfully reran. Because the pipeline was designed with idempotency, as discussed in Chapter 6, it correctly processed the 2 days of missing data without creating duplicates and updated the sales dashboard. In this case, robust logging, providing the specific error message, and a monitoring system that triggered alerts allowed for a swift diagnosis and resolution, minimizing business impact during a critical sales period. Key takeaways: ensuring continuous, healthy data flow. Monitoring, maintenance, and effective troubleshooting are indispensable parts of operating robust data pipelines. They transform a brittle data transfer mechanism into a reliable, valuable, and trustworthy asset. By treating your data pipelines as living systems that need constant care and attention, organizations can ensure the continuous flow of high-quality information, empowering swift, informed decision-making. As the data landscape continues to evolve, so too do the techniques for keeping these vital flows healthy, bringing us to the new frontiers of data processing. Chapter 10: Evolving Landscapes. Real-time, streaming, and advanced data architectures. The world of data is anything but static. Just a few years ago, daily or even hourly data updates were considered cutting-edge for many business operations. Today, the demand for immediate insights has grown dramatically, with many industries needing data in minutes, seconds, or even milliseconds. This push for immediacy, combined with rapid innovations in cloud computing and distributed systems, has fundamentally reshaped how we think about ETL and data pipelines. This chapter explores some of these advanced concepts and emerging trends, giving you a glimpse into the dynamic, forward-looking future of data flow. The next frontier: data at the speed of business. Traditional ETL, particularly large batch loads, where data is collected over a period and then processed all at once, is excellent for historical analysis, comprehensive reporting, and situations where some latency is acceptable. But what about scenarios where decisions need to be made now? Real-time versus batch processing, the need for speed. Batch processing. This is the traditional approach we've primarily discussed throughout this book. Data is collected over a period, e.g., a day, an hour, a week, stored, and then processed all at once in a scheduled batch job. It's highly efficient for large volumes and predictable, scheduled reports. Analogy: a delivery truck that picks up all outgoing packages from a warehouse once a day and delivers them. It's efficient for its purpose, but there's a delay between a package being ready and its departure. Real-time processing. This involves processing individual data points or small batches of data as soon as they arrive, with minimal delay, often in milliseconds or seconds. The goal is to provide immediate insights or trigger immediate actions based on the freshest possible information. Analogy: a continuous conveyor belt where each newly arrived package is immediately sorted and sent to its destination without waiting for others. The flow is constant and immediate, when real-time is essential. The shift from just-in-time to just as it happens data is driven by critical business needs. Fraud detection. Spotting suspicious banking or credit card transactions as they occur, allowing for immediate blocking to prevent financial losses. Personalized recommendations. Suggesting products, content, or services to a user based on their current browsing behavior, search queries, or newly added items to their cart. Live dashboards. Displaying up-to-the-second sales figures, website traffic, or stock prices for critical business monitoring. IoT, Internet of Things monitoring. Responding instantly to critical sensor readings from machinery in a factory, environmental sensors, or smart infrastructure devices to prevent breakdowns or respond to emergencies. Gaming and streaming. Updating leaderboards, managing player interactions, or adapting video quality dynamically in response to network conditions. Streaming ETL. Processing data continuously. To successfully achieve real-time insights, traditional batch ETL often transitions into streaming ETL. Here, the data pipeline is less like a series of sequential holding ponds and more like a continuous, fast-flowing river. Key concepts: events messages. Data is broken down into small, self-contained packets of information called events or messages, e.g., a single website click, a temperature reading from a sensor, a single financial transaction. Topic streams. These individual events are published to topics or streams, continuous, ordered append-only logs where data flows. Think of it as a never-ending queue of events. Consumers. Applications or processing engines subscribe to these topics and process the events as they arrive, often performing immediate transformations before loading them to a real-time destination or another subsequent stream. How it works. Instead of pulling large volumes of data periodically, streaming systems are designed to push individual data events as fast as they are generated. This requires specialized platforms and processing engines built for high throughput, low-latency data ingestion, and continuous processing. Data is processed in motion. Tools. Technologies like Apache Kafka for building robust, real-time data streams and publishing subscribing to events. Apache Flink, a powerful stream processing engine capable of complex real-time transformations. And Apache Spark Streaming, a module within the popular Spark Analytics engine for real-time data processing, are popular choices for building streaming ETL systems. ELT Extract Load Transform, a modern paradigm shift. While ETL has traditionally meant transform on a dedicated server, then load. A significant and growing trend, especially prevalent with the rise of powerful cloud-based data warehouses, is ELT. This conceptually flips the T and L around. Traditional ETL, the old way, extract raw data from source systems. Transform it using a separate, often dedicated ETL server or platform, performing all the cleansing, joining, and aggregating. Load the already transformed and cleaned data into the data warehouse or analytical database. Analogy. You take all your raw ingredients to a special, dedicated kitchen, your ETL server, prepare the entire meal there, and then bring the perfectly cooked meal to the dining table, your data warehouse. ELT, the new way. Extract raw data from source systems. Load the raw data directly into the data warehouse or data lake, often with minimal initial transformation. The data warehouse becomes the new staging area. Transform the data within the data warehouse itself using its powerful computing capabilities and native functionalities, like SQL queries. Analogy. You bring all your raw ingredients directly to the dining table, your data warehouse, which magically now has a built-in, super-fast kitchen. You prepare the meal there, using the table's own tools and immense cooking power. Why ELT is gaining traction? Leveraging cloud data warehouses. Modern cloud data warehouses, like Snowflake, Amazon Redshift, Google BigQuery, Databricks, are incredibly powerful. They can store vast amounts of raw data cheaply and have immense processing power to perform transformations directly within the database using standard SQL or specialized data transformation tools. This is often more efficient and cost-effective than managing separate ETL servers. Schema on read flexibility. In ELT, you load the raw data first. This offers greater flexibility because you're not committing to a rigid data structure up front. If business requirements change, you haven't invested heavily in a rigid transformation schema. You can simply retransform the raw data stored in your data warehouse whenever new needs arise. Agility for analysts and data scientists. Data analysts and data scientists can often access the raw data directly within the data warehouse or data lake, allowing them to perform their own custom transformations and explorations using familiar tools and languages like SQL, without waiting for data engineers to pre-process everything for them. This fosters greater agility and self-service analytics. Data lakes versus data warehouses revisited. Complementary roles. In the modern data landscape, data lakes and data warehouses are often not competing technologies, but rather complementary components within a larger data architecture. Data lake's role often serves as the initial, vast landing zone for all raw data, structured, semi-structured, and unstructured. It's a highly flexible, low-cost storage solution for future exploration, data science, and serves as the primary source for the ELT process. Think of it as the raw ingredient pantry for the entire organization. Data warehouse's role becomes the highly optimized, curated, and structured layer for reporting and traditional business intelligence. Data from the data lake is refined, cleaned, and transformed by the ELT process into the data warehouse to serve specific, well-understood analytical needs. Common workflow example. Real-time sensor data streams into a data lake extract. Selected raw data is loaded into a cloud data warehouse, load, and finally, powerful SQL transformations or specialized data transformation tools are run within the data warehouse, transform, to prepare it for dashboards and business reports. The rise of data mesh and data fabric, high-level explanation. These are more advanced architectural philosophies, recognizing the need for decentralized and interconnected data management in very large, complex organizations with many diverse data sources and consumers. Data mesh promotes the idea of data as a product. Instead of a single, centralized data team managing all data, different business domains, e.g., sales, marketing, supply chain, finance, own and publish their own clean, well-defined data products. They are responsible for making their data discoverable, addressable, trustworthy, and usable by others. Think of it as breaking down a central data team into smaller, specialized teams embedded within business units, making them more agile and responsive to local data needs. Data fabric, an architectural concept that aims to provide a unified, intelligent layer over disparate data sources, regardless of where they live. It uses technologies like metadata management, knowledge graphs, which map the relationships between different pieces of data, and AI to discover, govern, connect, and deliver disparate data on demand. The goal is to provide a holistic view of data without necessarily moving all data to a single, centralized location, opting for integration closer to the source. These concepts emphasize data discoverability, self-service access, high data quality, and clearer data ownership by the business units that create and ultimately use the data. Artificial intelligence and machine learning's role in data pipelines. AI and ML are not just consumers of prepared data, using insights from pipelines for their models. They are increasingly becoming integral components of data pipelines themselves. Automated data quality. ML models can learn patterns from historical data and then detect anomalies or deviations from expected patterns, automatically flagging potential data quality issues at scale, often before humans even notice. Smart transformation. AI can help automate parts of the transformation process, such as schema matching, automatically figuring out how different data fields across diverse sources relate to each other, data categorization, or even enriching data, e.g., extracting specific entities or sentiments from unstructured text like customer reviews. Predictive maintenance for pipelines. ML can analyze pipeline logs, performance metrics, and historical failure patterns to predict potential failures before they occur, triggering proactive alerts or even auto-correcting minor issues. Key takeaways: future-proofing your data strategy. The data landscape is dynamic and continues to innovate at a rapid pace. The shift towards real-time processing, the rise of ELT, the synergy between data lakes and warehouses, and the emergence of advanced architectural patterns all highlight a growing need for agility, responsiveness, and automation in data management. While the core principles of ETL, extract, transform, load, remain foundational, the tools, methodologies, and architectural approaches for implementing them are constantly evolving to meet the ever-increasing demands of an increasingly data-intensive world. Understanding these trends helps you appreciate where data engineering is headed and how forward-thinking organizations are future-proofing their data strategies. In our next chapter, we'll ground these concepts in real-world scenarios through practical case studies, bringing everything we've learned to life. Chapter 11, Data in Action, Case Studies and Real-World Applications. We've now covered the theoretical underpinnings of ETL processes and data pipelines, the what, the why, and the how of their components. We've seen how data moves, gets transformed, and finds its home, and how these processes are automated and maintained. Now, let's bring these concepts to life with a few simplified, illustrative case studies. These scenarios, drawn from common industry challenges, will demonstrate how well-managed data flows translate into tangible business value and solve real-world problems. Remember, these are narrative descriptions, not highly technical deep dives. The goal is to show the impact of ETL and data pipelines on various industries and how they enable critical business functions. Case Study 1. E-commerce personalization. Industry, retail e-commerce. Problem: an online clothing retailer wanted to move beyond generic product recommendations, people who bought X also bought Y, to highly personalized suggestions that truly resonated with each individual customer. Their customer data was scattered across their website analytics system, sales transaction database, and a separate customer survey platform. Without a unified view, personalization was difficult and often inaccurate. How data pipelines solved it. Extraction. A real-time data pipeline was set up to continuously capture website clickstream data, pages visited, products viewed, time spent on pages, items added to cart, as customers interacted with the site. Simultaneously, automated batch extraction processes pulled historical purchase data from the sales database and preference data from the survey platform overnight. Transformation. The raw clickstream data was cleansed, e.g., removing technical bot traffic, filtering irrelevant internal pages, and enriched with detailed product attributes, color, size, style. Historical purchase data was standardized and aggregated, e.g., calculating categories of past purchases, frequency of purchase, average spend. Customer survey responses were cleaned, categorized, and linked to customer IDs. All this disparate data was then masterfully joined and transformed into a unified customer profile, a comprehensive digital fingerprint for each shopper. Advanced algorithms applied to these profiles identified specific style preferences, brand loyalties, price sensitivities, and even predicted future purchase likelihood. Loading. The rapidly updating customer profiles and personalization insights were loaded into a real-time recommendation engine database, enabling instantaneous suggestions on the website. A copy was also loaded into the central data warehouse for deeper analytical insights and long-term trend analysis. Impact. Improved user experience. Customers saw highly relevant product suggestions, leading to a more engaging and efficient shopping experience. Increased sales. The conversion rate, the percentage of visitors who make a purchase, significantly improved, leading to a direct increase in revenue for the retailer. Better marketing. The unified customer profiles enabled highly targeted email campaigns and website promotions, leading to better campaign performance and reduced marketing waste. Case Study 2. Healthcare patient record integration. Industry. Healthcare. Problem: a large hospital system, formed through the merger of several smaller hospitals and clinics, faced a critical challenge. Patient data was severely fragmented. A patient might have their primary care records in one system, specialist visit notes in another, lab results in a third, and past medications in a fourth. This made it incredibly difficult for doctors to get a holistic view of a patient's health history, leading to potential misdiagnoses, duplicated tests, and inefficient care. Regulatory compliance also demanded a unified, secure view of patient history across the entire system. How data pipelines solved it. Extraction. Secure, compliant extraction mechanisms were established to pull patient data from diverse electronic health record, EHR systems, lab systems, pharmacy databases, and billing systems across all acquired facilities. This often involved complex integrations with older, legacy systems while adhering to strict privacy regulations like HIPAA. Transformation. Patient identifiers, names, birth dates, social security numbers, were carefully standardized and matched across various systems to accurately identify unique patients and deduplicate records. Medical codes, e.g., for diagnoses, procedures, medications were mapped to a common industry standard to ensure consistent interpretation. Inconsistent entries, missing values, and data entry errors were addressed, e.g., ensuring all crucial fields like blood type or allergies were present, and flagging if not. Historical patient interactions were aggregated to provide summary views, e.g., total number of visits per year, chronic conditions history, medication adherence. Loading. The fully integrated, standardized, and cleansed patient data was loaded into a central, highly secure data warehouse optimized for analytical queries. It was also made accessible, with stringent security protocols and access controls, to an operational reporting system used by clinicians at the point of care. Impact: better patient care. Doctors gained a comprehensive, unified view of patient history, enabling more informed diagnoses, reduced medication errors, and more effective treatment plans. Improved efficiency. Reduced administrative burden from reconciling disparate records, freeing up staff time for patient care. Faster research. Medical researchers could easily access large, consistent, anonymized datasets for studying disease patterns, treatment effectiveness, and drug trials. Regulatory compliance. The hospital could confidently meet strict healthcare data reporting and privacy regulations, like HIPAA, avoiding costly fines and maintaining public trust. Case Study 3. Financial fraud detection. Industry, finance banking. Problem: a major bank experienced rising financial losses due to fraudulent transactions via credit cards and online banking. Their existing detection system relied on batch processing, meaning fraud was often detected hours after it occurred. This prolonged delay increased the window for financial loss and made recovery difficult. The bank needed to identify suspicious activity in real time, within seconds of a transaction occurring, to block fraudulent activity. How data pipelines solved it. Extraction. A high-speed, real-time streaming data pipeline was deployed. It continuously ingested every transaction, credit card swipe, online transfer, ATM withdrawal, as it occurred from various banking systems, ensuring minimal latency. Transformation. Each incoming transaction event was immediately prepared, e.g., ensuring numeric fields were valid amounts, correcting minor formatting issues. It was then instantaneously enriched with contextual data from other financial systems, e.g., the customer's typical spending patterns, their previous geographical locations, the type of merchant, the time of day, current account balance. Complex real-time calculations were performed on the enriched data, e.g., is this transaction significantly larger than usual for this customer at this type of merchant, especially given their current location and recent spending activity? Machine learning models trained on historical fraud data were applied to calculate a fraud score for each transaction. Loading. The transformed transaction data, along with its calculated fraud score, or a suspicion flag, was immediately loaded into a real-time decision engine. If the score exceeded a certain threshold, the engine could block the transaction instantly or trigger an immediate alert to a fraud analyst. All transactions, flagged or not, were also loaded into a historical fraud investigation database for later analysis and model refinement. Impact: reduced financial losses. Fraudulent transactions were detected and blocked within seconds, dramatically reducing the financial impact on both the bank and its customers. Enhanced security and trust. Customers felt more secure knowing their accounts were actively monitored around the clock. Improved customer experience. Fewer legitimate transactions were falsely flagged, as the system could discern more nuanced patterns, reducing customer inconvenience. Case Study 4. Smart City Infrastructure Management. Industry, public sector urban planning. Problem: a city council aimed to become a smart city, by integrating data from various urban sensors and systems to improve citizen services and resource management. However, they had isolated data from traffic sensors, public transport GPS, smart streetlights, waste bin fill levels, and weather stations. Integrating this diverse and voluminous data manually was impossible, hindering effective urban planning and emergency response. How data pipelines solved it. Extraction. A network of specialized data connectors and APIs were configured to continuously pull real-time data streams from hundreds of city sensors, e.g., loop detectors for traffic flow, GPS trackers on buses, streetlight status monitors, air quality sensors. Batch processes collected less frequent historical data like waste collection schedules, energy consumption records, or long-term historical weather patterns. Transformation. Raw sensor readings, often technical and complex numerical values, were cleaned, standardized, and translated into meaningful metrics, e.g., vehicles per minute, average waiting time for a bus, streetlight power consumption, bin fill percentage. Geographical data, raw coordinates, was enriched with contextual information like street names, intersections, and specific neighborhood districts. Different data streams were integrated and joined to build comprehensive views, e.g., correlating traffic flow with bus delays and adverse weather conditions, analyzing energy usage patterns of streetlights relative to pedestrian traffic. Loading. The processed data was loaded into a central urban analytics platform and a city-wide operational dashboard. Specific real-time alerts were configured to trigger based on predefined thresholds, e.g., traffic congestion exceeding a certain level on a highway, a public transport vehicle going off route, a waste bin reaching 90% capacity. Impact, optimized traffic flow. Real-time traffic data enabled dynamic traffic light adjustments and informed rerouting strategies for emergency services during peak hours or accidents. Efficient resource allocation. Waste collection routes could be optimized based on actual bin fill levels, saving fuel and labor. Public lighting could be adjusted based on ambient light and pedestrian presence, conserving energy. Improved emergency response. Unified data views allowed for faster, more informed, and more coordinated emergency responses during critical events. Better urban planning. Historical data provided invaluable insights for long-term infrastructure development, public transit planning, and environmental policy decisions. Key takeaways: the ubiquitous power of well-managed data. These case studies, simplified as they are, powerfully illustrate the profound impact of well-designed ETL processes and robust data pipelines across diverse industries. They are the unsung heroes behind personalized online experiences, efficient healthcare delivery, secure financial systems, and smart city initiatives. They demonstrate that data, though a powerful resource, only truly unlocks its potential when it is meticulously extracted, intelligently transformed, and strategically loaded for action. With a clearer picture of data's purpose and impact in the real world, let's now look at how you can get started on your own data journey and where this field is heading next. Chapter 12. Your data journey begins. Getting started, further learning, and the future. Congratulations! You've navigated the unseen rivers of data, understanding how raw information is extracted, transformed, and loaded through robust pipelines to become the lifeblood of modern decision-making. You now possess a foundational understanding that many don't possess: the conceptual framework for how data truly flows in organizations, and the immense effort and ingenuity that goes into making it useful. This isn't an end, but a beginning. The world of data is vast, exciting, and constantly evolving. This chapter offers practical advice on how you can continue your learning journey, explore relevant skills, and glimpse the fascinating future of data engineering. Where do you go from here? Practical steps for aspiring data trailblazers. You don't need a computer science degree or advanced programming skills to start applying some of these principles in your own life or work. The most important thing is curiosity and a willingness to explore. Start small, data in your everyday life. Personal finance. If you use budgeting apps, consider how they extract transactions from your bank, categorize them, transform, and display them in a dashboard load. Can you manually replicate some of that transformation in a spreadsheet by classifying your own expenses? Fitness trackers. Your smartwatch collects raw sensor data, steps taken, heart rate, sleep duration. How is that data transformed by the app into calories burned, activity zones, or sleep quality reports? Appreciate the pipeline from sensor to screen. Organizing digital files. Think of cleaning up your computer's messy downloads folder. You extract files that don't belong, transform them by renaming or categorizing, e.g., photos, work documents, recipes, and load them into appropriate, organized folders. This is ETL on a personal, familiar scale. Public data exploration. Many government websites or research institutions provide publicly available datasets, e.g., weather data, population statistics. Downloading and exploring these in a spreadsheet can be a great way to practice basic data manipulation and discover insights. Explore foundational skills, no coding required yet, but good to be aware. Basic SQL, structured query language. This is the universal language for interacting with structured databases, as discussed in Chapter 2. You don't need to be a developer, but understanding how to write basic queries to extract data using a select statement, filter it using WHERE, and combine data from different tables using join will give you immense power. Many free online tutorials and interactive courses are available that allow you to practice without installing anything. Spreadsheet power. Master tools like Microsoft Excel or Google Sheets beyond basic entry. Functions like SUMIFS, COUNTIFS, text manipulation functions, and VLOOKUP are direct parallels to data transformation concepts. Pivot tables are powerful tools for aggregating and summarizing data. Data visualization tools. Get familiar with publicly available or free versions of business intelligence tools like Microsoft Power by Desktop, Tableau Public, or Google Data Studio. Understanding how these tools consume data and the importance of clean, structured data from pipelines will reinforce what you've learned. Hands-on exploration. Using free tiers and online courses. Many cloud providers, AWS, Azure, GCP, offer free tiers that allow you to experiment with their data services at no cost or very low cost for a limited period or up to a certain usage limit. This is a great way to gain practical experience with tools like AWS Glue or Azure Data Factory. Look for introductory online courses on platforms like Coursera, edX, Udemy, DataCamp, or Khan Academy that focus on data fundamentals, introduction to SQL, business intelligence basics, or even foundations of data engineering. Many provide hands-on exercises and simplified environments. Explore open-source tools mentioned, e.g., Apache Airflow for orchestration, as many have extensive free documentation and active community support for learning and troubleshooting. Further reading and resources, types of resources. To deepen your knowledge and stay current, seek out these types of resources. Online courses and tutorials. Search for Data Engineering Bootcamp, ETL Fundamentals, Data Pipeline Design, or specific tool tutorials, e.g., Oz Glue Tutorial, Apache Airflow Tutorial. Many provide practical, hands-on exercises. Developer communities and forums. Websites like Stack Overflow, Reddit, e.g., r/data engineering, r/data science, or specialized Slack Discord channels are great places to ask questions, learn from practitioners, and stay updated on industry best practices. Industry blogs and publications. Follow leading data engineering blogs from prominent companies, e.g., engineering blogs from Netflix, Spotify, Airbnb's data teams, or data technology vendors. They often share practical insights, architectural patterns, and emerging technologies. Official tool documentation. If you decide to dive deeper into a particular tool, e.g., Apache Airflow, DBT, a cloud ETL service, their official documentation is often the most comprehensive and up-to-date resource. Professional certifications. For those considering a career in data, cloud provider certifications, e.g., AWS Data Analytics Specialty, Azure Data Engineer Associate, Google Cloud Professional Data Engineer, or vendor-specific certifications can be valuable for validating your skills and understanding. Career paths in data engineering. Understanding ETL and data pipelines is your entry point into a rewarding and highly in-demand field. Here are some related roles that intersect with what you've learned. Data engineer. The primary role. These technical professionals design, build, optimize, and maintain the data pipelines and underlying data infrastructure, data warehouses, data lakes that data analysts, data scientists, and business intelligence teams rely on. They are often called the architects and plumbers of the data world. ETL developer. A specialized data engineer focused heavily on the extract, transform, load processes using specific ETL tools or scripting languages. Data analyst uses prepared data to answer specific business questions, create reports, and build dashboards. They are heavy consumers of well-built pipelines and often provide requirements for new data sets. Data scientist uses data, often prepared by data engineers, to build predictive models, discover hidden patterns, and uncover deep insights. They often need to understand the nuances of data quality and provenance. Business intelligence, by developer, focuses on creating interactive dashboards, reports, and data visualizations for business users. They often sit between data engineering and business analysis, translating business needs into data requirements and presenting insights. The future of data flow. AI-driven pipelines, ethical considerations, data democratization. The field of data engineering is continuously evolving at a rapid pace. Stay engaged, and you'll see these trends continue to shape the landscape. More automation and AI in the pipeline itself. Artificial intelligence will increasingly assist in designing, optimizing, and even maintaining data pipelines, making them more intelligent, self-healing, and adaptive to changing data. This could include AI that automatically cleans data or predicts pipeline failures. Greater focus on data governance and ethics. As data becomes more ubiquitous and regulations stricter, the importance of data privacy, security, and ethical use will only grow. Pipelines will need to incorporate advanced mechanisms for consent management, data provenance, and explainable AI insights. Real-time everything. The demand for immediate, actionable insights will drive further innovation in streaming data processing and real-time analytics, making instantaneous decisions the norm. Data democratization and self-service. Making data more accessible and usable to a wider range of users within an organization, reducing the reliance on highly specialized technical teams for every data request. Think citizen data engineers using intuitive, low-code, no-code platforms to build their own pipelines. Diverse data sources. New types of data will emerge, e.g., from advanced biosensors, digital twins, immersive virtual realities, presenting new formats and immense volumes needing to be managed and integrated into the data ecosystem. Conclusion: the power of flowing data. By empowering yourself with a conceptual understanding of ETL processes and data pipelines, you've equipped yourself with a fundamental literacy in the language of the modern business world. You now understand that behind every compelling dashboard, every personalized recommendation, and every strategic decision lies a diligent, automated process ensuring that data, the unseen river, flows smoothly, cleanly, and reliably to where it needs to be. This knowledge empowers you to ask better questions, make more informed decisions, and contribute significantly to your effectiveness in an increasingly data-driven society. Your journey into the fascinating world of data has just begun. Embrace the flow, continue to learn, and may your own data journey be enriched with endless insights.